Hello everyone. Today we will discuss the refrigeration, and this refrigeration will be achieved with the help of solar technology. So how we may achieve it, we will follow different basic methods and how to achieve. So let's discuss about the basics of refrigeration.
So what is refrigeration? We will first talk about that. Okay. So it is the branch of engineering science that deals with the transfer of heat. Actually, when we want to convert heat from a low temperature reservoir to high temperature reservoir, probably you all um, studied about the topics of say if we want to convert the energy from low temperature reservoir to the high temperature reservoir, then we talk there is requirement of refrigeration. And say it is T1, say it is T2, and here the condition is T1 is greater than T2. Okay, so if you want to convert heat from the low temperature reservoir to the high temperature reservoir, you need to do some effort on the system. Okay, the work must be there and must be greater than zero. Okay, so in that particular cases, you may achieve the refrigeration. Okay, so this is the basic requirement, and we were talking about that. So low temperature region to the high temperature region, then we require the air conditioning. Okay, I should change the yeah. So if we are using some of the process or the system to do this to achieve this, that is known as the refrigeration system. Okay, and the space which is to be cooled or will be maintained as the low temperature space will be is known as the refrigerated space. Okay, what are the units of refrigeration? So basically the unit of refrigeration is ton of refrigeration, and how it may be defined, we'll talk about that. So a ton of refrigeration is defined as the amount of refrigeration effect produced by the uniform melting of 1 ton, where 1 ton is refers to the 1 US ton or 1 short ton. Okay, which is equal to 907.18 kilogram instead of 1000 kilogram. So very important thing which needs to be taken care is that this ton is not equal to 1000 kilograms. Okay, because this refrigeration initiates from the American region, so we have to use the ton, the value of ton used by the Americans. So American ton or short ton or US ton is equal to 907.18 kilograms of ice from and at 0 degrees Celsius in 24 hours. So we need to understand what do you mean by this. So actually, we just want to uh, have something like say this is 1 ton, okay, of ice. So 1 ton of ice when converts to 1 ton of water, 1 ton of water. Okay, then then this conversion, if this conversion is being done within 24 hours, if this conversion in being done in the 24 hours and at the value of 0 degree of Celsius, then this conversion will require some amount of heat added to the system. Only then it is possible that if we are converting ice into water, we need to have some heat to make it done. Okay, and definitely you all know that the heat will be in form of latent heat. So the latent heat is required to be given to the system to convert into water equal amount of mass in 24 hours. Okay, so if I want to convert this talk in terms of say formula, then 1 tr must be equal to something, say 1 US ton means 907.18 kilograms into the value of latent heat of vaporization. sorry, latent heat of condensation, that is equal to, or the melting, sorry, not the condensation, latent heat of melting or latent heat of freezing, that is equal to 335 kilojoule per kg. Okay, over the time of 24 hours. So when we'll convert this, we get approximately 12,400 kilojoule per hours. Okay, because this cancel out, and if we again divide this by the say 60, we'll get it like approximately the value will be 210 kilojoule per minutes, and this may also be termed in terms of say 3.51 kilojoule per seconds. And we all know that the kilojoule per second is nothing but the kilowatt. So this may also be termed as this. Okay. So one TR value is equal to 3.51 of kilowatt. So roughly we may use this term that if we are using 1 TR capacity refrigeration for 1 hours, then it will consume around 1 kWh. Sorry, how much kWh? So the value will be 3.51. 3.5 kWh will be the answer. Okay. So this is what we have already discussed and gone through. So if we talk about the performance of a refrigerator, what is the performance? What is how we may calculate it? Okay, what is the performance parameter here? So the parameter we usually use is efficiency. So we say efficiency. The very rough formula of efficiency is say output by input. So how much we output we are getting instead of how much input we are giving to the system. Okay, so the efficiency may be calculated with this method, but for proper methodology or proper getting the answers, the correct formula is desired output over required input. Okay, but what happens when we talk about the efficiency? The desired output it is, and in compared to the required input, when we are using the same method, same formula to get the performance in the refrigeration, the value goes more than one. So to avoid any confusion between the efficiency in other methods, other systems, and efficiency of the refrigeration systems, the new performance parameter has been created, and that is COP. This is not today's value. This is not the today's performance parameter, but whenever they have created, this was the reason. Okay, so here the performance parameter may be calculated with this formula. Again, the formula is same, only the name has been changed. Okay, so the desired output of ours is the low temperature heat rejection, and the required input is the WNet. Why you have converted this WNet into the QH minus QL, or should I tell about that WNet has been accepted as this? Because we all know that the according to first law of thermodynamics, we all know that this happens. Okay, so Q net will be equal to W net according to first law of thermodynamics. And that is why we may calculate W net in terms of Q higher minus Q lower. Okay, so in that way, we may get the value of this one. Okay, so conversion of this value into the another one may be done like this. Okay, a very important thing is here is these all cycles are anti-clockwise, as these are energy consuming cycles instead of energy producing cycles. Okay, so the applications of refrigeration, preservation and transportation of food products, used for air conditioning purposes, preserving life-saving drugs, vaccines. Nowadays we this word is very familiar because of the COVID vaccines. Okay, and other medicated solutions. Used for making ice products like ice creams and other products may be there. Used for efficient operations of servers, special machining, and other workstations. So these are the basic example: ice plant, air conditioning, cold storages, and refrigerators and all. If we little talk may be required for the refrigerants, what are the refrigerants? What are the basic properties a refrigerant must have? Okay, so working fluid used in the refrigerators are known as the refrigerant. Okay, refrigerant may be classified in two of the very important parts. Or so first will be the directly take part in refrigeration system, as freon 1 to another freons. And if you talk about the secondary refrigerants, so the refrigerants which are first cooled by the primary refrigerants. So these refrigerants are actually not taking directly part into the system. They are first cooled by the some another refrigerant, and then they are cooling the required things. So examples may be like brines, sodium chloride, calcium chloride, ethylene glycol, propylene glycol, and etc. Okay, if we talk about the properties of a refrigerant, so multiple properties are very required and very important here. And so first is the ODP, ozone depletion potential. uh, you all know that any of the material, if depleting the ozone layer, that must not be tolerated. So definitely it is governed by the Montreal Protocol. The ODP of the refrigerant should be equal to zero. If it is more than one, it should be eliminated. It should be reduced somehow. Okay, and must be in the limits provided by the uh, different climate authorities. Okay, so if you talk about the global warming potential again, it must not have a very good or very bigger value. It must be negligible or the insignificant. So refrigerant should have as low as GWP, global warming potential. जितना कम होगा उतना ही बढ़िया है. Okay. So it should be a non-flammable, non-explosive, non-toxic, chemically stable. We are using chemically stable because during this operation of refrigeration, what happens, the pressure range is there, in high pressure to low pressure is there, and temperature is also varying to a particular range. So in that particular pressure and temperature range, the refrigerant must not lose its basic or important properties. Okay, chemically stable means the chemically reactiveness must not vary, and if it is behaving like it is say maybe if it is flammable or explosive, or it is behaving like a toxic, so it may create a problem for us. Okay, so latent heat of refrigerant, it should be very high. It should be non-corrosive to the metals. The pipings we are using, the different valves we are using, coils we are using, should not react with them and should not be corrosive. Okay, and if we talk about the boiling point, freezing point, they should be very less. Okay, so first we need to talk about the basic methods of refrigeration we use. So first is the vapor compression refrigeration system. Another is we talk about the vapor absorption refrigeration system. Okay, this is frequently used system. And if we talk about the uh, other than the frequently used system, these are most costlier also. Why we use vapor absorption systems? These are not frequent. Installation is very costly. Installation is costly, and these are not frequent. These are comparatively, the running cost is very low. Okay, so these are the important things which needs to be taken care. And so vapor compression refrigeration systems, if we talk about these two, we'll find a first vapor compression refrigeration system, that how it behaves, how it works. So first we talk about the working of the VCRS system. So it will be easier to get the cycles and working of the VARS systems and solar refrigeration system thereon. Okay, so there are four important components. First is the evaporator. Okay, so if I want to highlight this, so first is the evaporator, which is the main component. There are multiple coils. In these coils, the uh, refrigerant in the liquid form flows, and over these coils hot air of the room goes to the coils, get some energy released to the coils, and after being cooled, converting it to the cold air, it again recirculate to the room, hot room, I may say. Okay, or the place where we want to get the refrigeration. Okay, so after converting into vapor of the refrigerant, these refrigerating particles moves to the compressor. We all know that the compressor is used to increase the pressure of the gases. So when we will increase the pressure of the gases, and here the gas is nothing but the refrigerant. So when we do this, temperature also increases. And during this process, when the temperature and pressure both increased for the refrigerant, it went to the condenser. In the condenser, we want to reduce or lose the heat to the environment. This heat normally behaves or should be in terms of latent heat only, but we want to reduce the sensible heat also. Okay, so that the work for the expansion valve reduces, and later on the very small amount of work needs to be done with the help of expansion valve, which is actually not very small, because the temperature and pressure both decreases during the expansion here. This follows the concept of Joule Kelvin effect, probably you all know that. And then it went back to the evaporator. Okay, so I just want to tell you about the uh, conditions of refrigerant here, which is very important if we want to discuss that. So at the point number 4, or if I am talking about the before the evaporator, what are the conditions of refrigerant? So it is a low pressure, low temperature and liquid. Okay, low pressure, low temperature, liquid. This is about the refrigerant. Okay, so when it goes to evaporator, this low pressure and low temperature remains constant, but the liquid refrigerant converts to the vapor. So here low temperature, low pressure and vapor refrigerant, vaporized refrigerant, or I may say that this is in the gaseous phase. Okay, so this gas when goes to compressor, the initial purpose is to increase the pressure, but the temperature also increases. So here you will get high pressure, high temperature gas. And gas is again the same, that is vaporized refrigerant. Okay, when it goes to the compressor, it loses the uh, sensible heat and latent heat both. While in case of evaporator, the only gain is was via latent heat. यहाँ पर हमको सिर्फ latent heat gain मिला था, but we are losing here latent heat and sensible heat both. Okay, and after that it goes to the expansion valve, or after condensation I may say this is the condition of high pressure and the moderate temperature. Moderate temperature is because of the latent heat loss is there, but sensible heat is also lost. Okay, so this temperature, moderate temperature, or I may use the intermediate temperature. Okay, and the condition of temperature is, so we have discussed, and that is the liquid. This is in the liquid form, or actually this is mixture of liquid and gas both. So we may assume that this is the liquid. And but after just if we no, actually this must be in liquid form only, because this is the point where we want to achieve. I will discuss this also. So after point number 3 to 4, when we move in the expansion valve, again we get the low pressure low temperature liquid. Okay, this is the line explained for the calculation or understanding of the high pressure and low pressure zone. So just after the compressor, we reach to the high pressure zone. Before the compressor, we are in the low pressure zone. Just before the this expansion valve, we were in the high pressure zone, and just after this, we were in the uh, low pressure zone. Okay. Another thing which is very important here, we need to talk about that also. Yeah, and that is say if we are talking about the TS diagram, temperature entropy plot, then we'll get this is the vapor dome for the refrigerant, and here 1 to 2 is the compressor. Okay, this is the portion where we talk about the compressor. This is in condenser. So you are able to see here that in condenser we lost the latent sensible heat also. So the temperature decreased here. So this is the sensible heat loss to the environment, while this is the latent heat loss to the environment. Okay. So after the condensation, we reached the the uh, saturated liquid state. So at this point, definitely it will be in the liquid. Okay. 3 to 4 is the throttling process that happens in the expansion valve. In the domestic refrigerators, we use capillary tubes basically for the expansion. So this is the domestic refrigerator. Uh, Probably it is not to be discussed, but for the example purpose only, I have included in my PPT. So if somebody wants to get the better understanding, so this is the portion of refrigerator where we talk about the refrigeration box, which is evaporator, which plays the role of evaporator. The outlet of this goes to the compressor. So this is the lower back portion of our refrigerator, which is normally hermetically sealed to prevent noise and heat loss to the environment. After this compression process, the heated, high pressurized refrigerant goes to the condenser where it loses latent heat and sensible heat both. And again, it went to the expansion valve, and after that, cooling liquid, low pressurized, low temperature refrigerant goes to the uh, evaporator. Okay, so this is the vapor compression system. The very important thing we should talk about the vapor absorption, I'm sorry, vapor compression refrigeration system is that these systems are, quite costlier. So to reduce the cost, what we may do? So first thing we may do is somehow if we want, somehow if we are able to reduce the energy consumption created by this compressor. Okay, we all know that compressor is a device used to increase the pressure of the gases. Okay, and this this device consumes so much of energy. So if we are able to reduce the energy consumption by the compressor somehow, then definitely we will be able to increase the performance parameter or COP of the system. Okay, so that is a prime requirement by us. So how to reduce this? So multiple methods of energy enhancement applied, but the very efficient and prominent method was suggested by the research of the vapor absorption refrigeration system. So what are the vapor absorption refrigeration systems? So these are the systems which tells you that if you are not changing the first three components of the left side of this line, these three are same. Condenser is same as it is as previous. Okay. This expansion valve is same as previous, and evaporator is also same as previous. What we are changing? We are changing or replacing the whole bulky right side system, okay, to reduce the energy consumption which was demanded by the compressor. So this is our requirement, and how it actually works we will discuss about that. Okay, so say I'm taking some example to explain this figure. Assume that our refrigerant here is the ammonia. Okay, we all know that this ammonia is having very good solubility in the water, very good solubility in the water. Okay, and whenever ammonia mixes with the water, the exothermic reaction takes place. What happens? The exothermic reaction takes place means heat is released to the environment. Okay, so if we want to increase the absorptivity of ammonia in water or solubility of ammonia in water, you want to, or you need to decrease the temperature of the solution. If you will be able to make it, then definitely the absorptivity or the solubility will increase, or the concentration of ammonia in the water will increase. So what will happen? So low pressure refrigerant vapor absorber moves to the absorber. Okay, say ammonia is going here and water is already available there. Okay, so water is here and we are moving ammonia from here. Then what will happen? This will mixed out and the ammonia vapor will mix with the water, because you all know, we have already discussed that the evaporator releases the refrigerant vapors of refrigerant. So the vapor of ammonia moves to the water liquid, mixes and heat liberated to the system. If we are dissipating heat in the very good manner, definitely this solubility will increase. Okay, then after this solution is here, so the solution is say ammonia plus water. Okay, this solution goes to the pump, because this is the liquid now. And how we may increase the pressure of a liquid by using pump. So why we are using pump? Somebody may say, sir, you are replacing the compressor and using the pump. So why there is a requirement we are somehow using the electricity? Yeah, definitely we are using electricity. But we all know that the energy consumption by a pump for the same amount of volume will be very, very less in compared to the energy consumed or energy consumption by a compressor for the same amount. And this will be huge difference. Okay, so this huge difference uh, is moving us in this direction to use the vapor absorption refrigeration system. So by using pump, the solution pump actually pumps this mixture. So after pumping, this mixture went convert to the high pressurized solution. Okay, so this is the HP solution. This was the LP solution, low pressurized solution. So this high pressurized solution goes here in the generator. In generator, what we are doing? Steam or hot water is passed through this solution. So this steam or hot water somehow increase the energy of the solution. And I told you earlier that when this ammonia mixes with the water and exothermic reaction takes place, heat releases to the system. If you want to increase the solubility, you need to decrease the temperature. If we are increasing the temperature here, it means we are again separating the ammonia and water. So ammonia vapor will move in this direction. Okay, and water of high pressure will again come back. So when it will move here, it is a high pressure water. So high pressure water uh, will not mix properly with the low pressurized water. So we want to reduce the pressure of the water, or some ammonia may also be mixed in this. So this passed through the pressure reducing valve, and after passing with this, uh, this mixes with the absorber water. Okay, one or two very important terms are also written here which needs to be discussed. This solution is known as the strong absorbent solution, while this solution is weak solution. So why you are telling that this is a strong solution? It has a reason. We all know that solution is made up by the mixing of solvent plus solute. Okay, so what is a solute? Solute normally is in the very small amount, while solvent is something which is dissolving the solute inside it. Okay, so our solvent is water and our solute is ammonia. So in the absorber, if we made a very good combination, very good solution, then the percentage of ammonia was better in the water. So this was a strong solution. Okay, after moving from the generator, the ammonia vaporizes and moves to the condenser, while the very less amount of ammonia mixed with the H2O came back to the absorber again. So definitely this solution must be the weaker solution. That is why this is known as the weaker solution or weak solution. Okay, so this is very important. That is why we are talking about that the solution is very important, and we need to talk about the weakness and strength or strongness of the solution. So these are the reasons why we use these words. Okay, and the remaining fundamental is same, so no need to discuss it again. Okay, probably you are getting. Okay, so this is the very important thing. Now, we have already gained the fundamental of why we are using VARS instead of VCRS. Okay, so in case of vapor absorption refrigeration system and vapor compression refrigeration system, here energy consumption is very, very high, very, very high. While in case of vapor absorption refrigeration system, energy consumption is very small in compared to this. Okay, another thing, the basic problem associated with this vapor absorption refrigeration system is the installation cost is very high. While here installation cost is not very huge. Okay, so we want to reduce this system, and if somehow we are able to reduce this also, किसी भी प्रकार से अगर हम इसको मिनिमाइज कर दें, एकदम जीरो कर दें, then this will be one of the best method. Okay, so we need to try, and we tried the same in our topic. Okay, so we will talk about the solar refrigeration. So how the solar refrigeration will work? So in case of solar systems, we will get the energy for heating in the generator, heating in the generator by solar radiations or solar systems. Anyhow, the any type of solar system may be there. So actually the input is solar radiations, which is of zero cost for us, and this solar radiation goes to the generator, heat up the solution, separates the system. So our energy input in the generator will become zero. Okay, so this is the basic fundamental. So our focus will be on the solar generator, and for the solar generator systems, we will talk about this only. Okay, so how it works, we'll talk about that. So this is the first I will talk what we have already gone through, and then we'll talk about what we need to discuss and what is newer to the system. So this is the evaporator. Okay, this is the evaporator where hot gases comes inside over the cooled coils, gets cooled, and then move to the room where we want the cooling. Okay, after the evaporator, it goes to the absorber. In absorber, we have seen that there is a pump. So this is the pump. Pump goes to the uh, pump sends this pressurized liquid to the generator. Okay, so when it is pumping, it is increasing the pressure. And actually we want to increase the temperature of the fluid also, because in generator definitely we need to heat it. Okay. And we also know that after generation, after the generator, the weak solution water needs to be resent to the absorber. So here this is the heated water, and here this is the cooled solution from the absorber. If we make a heat exchanger here, so it will reduce the heat input in the generator, and it will also beneficial for us, because it needs to be, it will not take any more requirement to cool the weak solution before the absorber. Okay, because again, in case of absorber, if we want efficient operation, we need to cool here. So it will be better if we will cool this process here, if we cool the solution here before reaching the boiler or generator both. Okay, so a solution heat exchanger is added here to increase the efficiency of the system. So this is nothing but this is one of the heat exchanger extra added to the system. Okay, and then after generator, heat is uh, transferred, and we will discuss how it transferred. First we just discuss what we have already gone through. Okay, so generator, after generator, the vaporized refrigerant again sent to the condenser, and in the condenser, what we do, we cool the system. And the how we may cool the system, uh, whatever is the energy taken from the refrigerant here, this needs to be sent to cooling tower. In the cooling tower, what happens, probably you all know, but still I'm explaining this. So cooling, in the case of cooling tower, we actually make a pipe arrangement and spray. Multiple spray systems are used, okay, which actually converts this drop into a very smaller drops. So there are multiple things happen in the cooling tower. So first is splitting of a one bigger drop into multiple smaller drops. This makes the cooling. Probably you have felt in the salon, somewhere whenever you move to salon, what a barber do, he sprays water on your face, not on your face, basically on your hair. So some drops on your face feels cooler to you. Even the water is not so cooled. Okay, so when a bigger drop converts to very small multiple drops, it releases energy, it feels cool down. So the temperature decreased here because of the first reason. Second reason, when the water vapors, drops are moving in the downward direction because of gravity. Actually, what happens? The cooling tower shape is like this. Okay, in the bottom area, you find that the area is larger. More area means more pressure. More area means more pressure. So high pressurized air move from the here. High pressurized air move from the here. Okay. And low pressurized air in the, this is the low area, low pressure. And you all know that the flow of any fluid usually happens from high pressure to low pressure, high pressure to low pressure. Okay, so when the drops of the spray, I should use a different color. So when the water drops are moving in downward direction, after interaction, some of the heat released to the air going in the upward direction. Okay, so air molecules will move in the upward direction because of the pressure difference, and water molecules are moving in the downward direction because of the uh, gravity, because of the more weight of the water molecules. Okay, so this cross ventilation, cross movement, heat transfer takes place here and this water cools. So this is the second reason. And the third and very important reason which is responsible for the huge temperature difference in the system is that when we are moving in the downward direction, what happens? Evaporation takes place. What happens? Evaporation takes place. So evaporation makes a very important role here. And how it happens? First, we need to think. So what happens when the molecules, when the water molecules are moving in the downward direction, they are coming in contact with the air. So say air, the temperature of air is not much, okay, and air is coming in contact with the water molecules. Okay, so the upper or outer molecules of the water will try to convert into vapor. Okay, but they don't have that much energy to convert into vapor. So they takes energy from the adjacent molecules, adjacent drops, and during this process they will cool down the remaining molecules. Are you getting? This is the process. So out of that continuous movement coming in contact with the air molecules, this process will continuously you know iterative process like things will happen, and because of this the continuous conversion of water molecules into vapor will takes place, and this evaporation will definitely decrease the temperature of this water to the WBT. Okay, probably you all know what is WBT. This is wet bulb temperature. So it initially it was the condition of DBT or the higher temperature, but by this method we may achieve to this extent. Okay, so I'm again reminding you there are three basic reasons by which we are able to decrease the temperature of water molecules. First, conversion of a bigger drop into smaller ones. Second, by um, contacting um, with the hot air going in the upward direction, and third is the evaporation. Okay, so by these three methods we are able to convert this uh, high temperature water into low temperature water. So after cooling tower, again this cold water the comes to the system. By pumping, we send this in the absorber to cool the system, cool the solution. Again, it moves to the condenser. Okay. So with the help of a single channel, we are doing the same. We are doing the both. Okay. So probably you got this. You got this. So one cycle of this arrangement we have already discussed. We have discussed these things. Now we need to talk about this. So what happens before generator? Here, the left side motion needs to be discussed now. Okay. So what happens? We need heat in the generator, but this process may be done only in the zone where if we are getting some energy. Okay. So for that, we have made some arrangement here. So here the sun is there and liberating very much energy for us. So this energy is collected by the collector array. Okay, so the collector array consumes the energy. Okay, and after consuming this energy, the fluid the fluid which was moving inside the absorber tubes, which moves to the relief valve, and then this hot fluid, maybe actually I'm not naming the fluid because any fluid may be there. If we are getting that any fluid is having very good thermal mass, or maybe very good for us, non-corrosive and some another thing, so we may take any other fluid. Okay, so it is not necessary that we are using water only. So that went to the main storage tank. Okay, and again pump may be required for this, because actually this collector array is already, it is being told that this is an array. This is not a collecting pipe or selector, solar collector plate or anything else. So multiple pipings may be there, pressure drop may be there. So to lift the water, we may have a pump. Okay. Uh, so a feedback system may also be attached for this. So control system is attached here. So main storage tank is here in which the hot fluid is filled. So where from this hot fluid came? This is the fluid which was in contact previously with the collector array and now stored in the main storage tank. Okay. Now it is being circulated to the auxiliary heater. I'm sorry, not auxiliary heater. I will tell you why we are using it. This is circulated to the generator because this is heated very to a very good extent. This heated fluid moves inside the generator. Okay, then it heats up the solution inside the generator, and probably you have remembered what is inside this. In generator we have ammonia plus water. Okay, so this is nothing new with respect to this one. We were talking here also. In the generator we had ammonia plus water. After getting heat, the ammonia separates from the water and moves away to the condenser. So similar things will happen here, that ammonia plus water is there. After heating provided by you from this tank, this ammonia moves here in the condenser and water moves here in the absorber via solution heat exchanger and this expansion valve. Okay. And say after giving heat to the ammonia and water solution in the generator, this hot fluid moves to the pump, and after that it moves to the main storage tank again for the heating. So now a very important thing is there, which is auxiliary heater. Why we need it? First thing, uh, you know um, they are not the situation like in India everywhere. We are so fortunate in India that we are getting solar intensity every day in a good intensity also. Okay, so good value is there, and because of this very good solar intensity, we may rely more in compared to other countries, cold countries, on these solar radiations, because probably most of the days, around 300 sunny days, we have solar intensity around 800 watt per meter square and more. Okay, so that's a big deal. Even for today, if we are talking about say solar radiations, today morning there were no sun rays with this much intensity, but currently around 500 watt per meter square radiations are available in the Jaipur also. Okay, so the very important thing needs to be discussed here is, because we talk about the solar radiations, these all are not so much reliable everywhere. So to make the system more reliable, if some day is not the sunny day, then what to do? For that particular cases, we need a auxiliary heater. So if this solar system will not work, the heater will work. Okay, so definitely, because this is the parallel system, we don't want to use it every day, because otherwise our performance parameter will decrease. Okay, so for that we need to have a auxiliary heater. So probably you got this figure properly. We need to move again. So glimpse over solar absorption efficient system. So compressor is replaced by absorber. We have already gone through, so probably this slide is very easy for you all, because we have already discussed that compressor previously was replaced by absorber, the pump, solution pump. Okay, this is the solution pump, the generator, and the heat exchanger. The heat exchanger is the uh, solution heat exchanger. Okay, Here we have also used another thing, which is pressure reducing valve. So you may also add up that. So pressure reducing valve. Okay, so heating is done by solar collectors here, and for the non-reliable systems, you may talk about the auxiliary heaters also, which I will definitely not recommend in the India. Okay, so due to the intermittent nature of the available solar energy, a hot water storage tank is needed. This is very good. Why we are using it? Because to reduce the uh, intermittent supply of solar radiations. Another thing, if somebody wants to use the system for a comparatively longer hours, okay, say no doubt the solar radiations are available to at least around 10 hours and more, but for some available more available hours we may use it if we are having a solar storage tank. So that's a good deal, that's a very good deal. And then we talk about the lithium bromide water system. So lithium bromide LIBR and water system. This also be one of the system in which lithium bromide is the absorber and water is the refrigerant. Okay. So this is just like ammonia water system. So ammonia is the refrigerant and water is the absorber. Okay, so this is one of the another refrigeration system for the vapor absorption systems. So system generally operates at a generator temperature in the range of 70 to 95 degrees Celsius because of the limitation of water. We normally tries to move within 0 and 100 degrees Celsius. The low temperature limit is this. So the lower limit of temperature is 110 in ammonia water systems. So it may vary according to which type of refrigerant you are taking. So that is not a very important, um, that which type of refrigerant you are liking. It may also be the reasons that which is more available around you, which is more cheaper, or corrosion and other parameters are also important. Okay. So now we need to talk about the classification of solar vapor absorption systems. We need to classify. Okay, we need to classify on the multiple basis, because after the classification, after the comparison, we will find that which is better or which is little less better. Okay. So on the basis of refrigerant or absorbent, we talk about the lithium bromide H2O system, ammonia H2O system. I have already gone through. Okay. Now we need to talk about the on the basis of solar collectors. So evacuated tube collector we may have, and parabolic trough collector we may have. So we'll discuss how the systems are used in detail. Okay. And on the basis of stages of regeneration, the single effect may be there, the double effect may be there. Okay. So the single effect stage of refrigeration is used for the when you are having a single effect, means a little connection or little meeting with the solar radiations, while in case of double effect we talk about the more connection with the solar radiations, uh, more connection with the um, solar effects. Okay. So first, if we talk about the on the basis of refrigerant or absorbent, so these are the things where I have already talked about this. So lithium bromide and H2O system, where refrigerant is the H2O, while the lithium bromide is the absorbent. Okay. So and in the case of ammonia water system, ammonia is the refrigerant and water is the absorbent. So we have already gone through. Now we need to talk about the evacuated tube collector. So first, and this is very important, we will talk about evacuation also. We'll talk about some other parameters also, which will be used here. And okay, yeah. So evacuated tube collector and how it works. So experimental setup. If we talk about the experimental setup, So this is the experimental setup. This is the sun. Okay, these are the radiations imparting on this system, and this is the um, evacuated tube collector. This one is the collector. How this collector consumes the energy, how it releases the energy to the fluid, we'll discuss about that also. First, the incident solar radiation, which is known as the insolation. Incident IN, solar SO, and radiation, so TION. So this is known as the insolation, and insolation is uh, very important parameter, because I have told you that it depends for which type of geometry or which place you are talking about. Okay, so in that particular zone, in that particular condition, we needs to talk about that. Okay, so here ammonia water system is there, and this place is Turkey. Okay, where Adana is the place, and capacity is 1 TR. So 1 TR power plant is this, where we are talking about the. This is actually not power plant, but the system actually. Okay, so what we are doing here, this is our evaporation, this is our evaporator, this is absorber, this is solution heat exchanger, this is pump expansion device, this is strong solution, this is weak solution, this is generator, and this is condenser expansion valve evaporator. So these all topics are already has been discussed. So we need to talk about the newer one. So this is generator, and we are using the evacuated tube collector. So what is the evacuated tube collector, and how it actually converts the energy to the fluid? We will discuss about that. So yeah, so this is the evacuated tube collector, and in this actually there is this glass tube with vacuum. Okay, and as we are talking about the glass, so here the vacuum inside the glass tube. This shaded gray portion is the absorber sheet, and inside this the pipe is the heat pipe. Probably you know what is a heat pipe. Heat pipe is a device which which converts approximately 100%, and this is nothing but a heat exchanger. So these are very efficient heat exchangers. When we talk about the heat pipes, so these heat exchangers are very efficient heat exchangers. Normally the efficiency is more than 95%. Okay, even after little exercise you may achieve this. So these are very efficient heat exchangers, and after making the system evacuated, you actually tries to move around this, because when you are evacuating something, the convection heat losses will remove. Okay, so and we all know that in the open areas convection heat losses are maybe huge. So to reduce that, we made it evacuated. Okay, so when hot liquid moves inside, and this hot liquid comes here, and here the cold fluid come here, gets the energy from this tank or the heat exchanger, goes to the system. Okay, and by making this system, we are making our system more performing, and definitely COP may increase. Okay, so the performance temperature diagram of the absorption system. I hope this diagram is very clear and easy. So here, evaporator we have already discussed. Absorber is a system where heat is released to the system, by the system actually. Then the solution pump, then solution heat exchanger, then generator, and it will again move it in this direction. And here in generator we are hitting with the help of this system. So this will become most efficient. Okay, so if you want to get conclusion of this system of the Turkey, so we were talking about. So this is the 1 TR um, refrigeration system. So during the fairly change during the day, the COP is in the range of 0.2432 to 0.454. That is not a very poor. That is very good if you are using any alternative non-renewable energy system. So that's a big deal, even for a 1 tier system. If you are getting this is definitely very appreciable. So all the CAP values are decreasing with decreasing generator temperature. Definitely it must, especially the COP becomes considerable low as the generator temperature value is lower than 110. Okay, the maximum solar collector efficiency is calculated as 0.784 at 1 p.m. for the solar IR radiation intensity of 719. See, this is the thing I want to emphasize on, that the value in Turkey is 719 watt per meter square, which is not very high. In Rajasthan, we may have very good solar intensity normally. Okay, in summer days, we may have around 1200 watt per meter square. So lesser heat losses and better performance than flat plate collectors. If we talk about the parabolic trough collector, so this is the parabola. On the focus of this parabola, there is a absorber tube. So if any solar radiation comes here, it is reflected to the absorber tube, and because of this, the heating, or I should say, the overheating of the tubes, very good heating of the tubes may happen with the help of this approach, and this heated fluid goes to the storage tank. This heats inside the generator, okay, and make the system more working and proper without any use of say auxiliary heater and all, and then it goes again to the pump. Okay, then here also we may have a pump. So pumping may be required in all the processes because we need to move a liquid. So without gravity use, it is not very efficient, because thermosiphoning will not be very efficient here if we are not using pump. Okay, the battery information is here. The lithium bromide H2 system were used. Okay, and is it was in the Iran 5 TR capacity system. So in both the systems we have gone through that the multiple um, options and better options are there. Okay, so the thermal losses of absorber tube of collectors, what are the losses is, how we may reduce it. So these losses are, say, this is the reflector. Okay, so this is the outward portion where glass tube is there. So radiation losses may be there from the inside and outside. Okay, but the convection losses are from the upper glass tube only, because inside there is evacuation. Okay, and in case of say parabolic trough collector also, we will not have a huge amount of convection losses from but because in compared to that, radiation losses will be quite higher, and conduction losses during this zone, because this is the made up of thick sheet. This is the absorber tube inside, and in which the working fluid moves. So these are the optical losses and all. Okay, still this is beneficial because we are concentrating the things, concentrating the radiations to a particular tube, which is quite efficient. Okay, many solar collectors work on this, are very efficient. So the results of this system was connected with this. So this diagram is sufficient to explain this, what we may achieve. So this continuous line is for solar heat gain. So this is the solar heat gain in the Iran we were talking about. सुबह के 5:30 बजे से ही बहुत ज़्यादा धूप हो जाती है. So in morning 5:30 around, there is solar radiations till the 6:30 in the evening. Okay, and the generator heat load was say starts from the 6:30 and to the 7 in evening, and cooling load in morning is very small, 5 kW only, while in the evening time or it peak arrives around 4 to 5, where it reaches around 15 to 16 kilowatt. So during this we may find the requirement of, or the actually rectification of the requirement may be managed. So, and here, if you talk about the COPE, and July and September both are given. So, in July, they said that the solar time hours are also represented there. Uh, pardon. Yeah, the solar time hours are around, say, when solar time was around 14 hours, it was around 0.76. COP is very good. Yeah, that is very appreciable. And definitely when we have more solar hours around 19 or 18, this value is 0.76 or 77. So that's a great achievement. With these non-renewable resources, we are getting this much of COP, that is very appreciable. Okay, so if we talk about the conclusion, there is no requirement. We have already concluded in this way for the comparison. So for the evacuated tube collector, when the absorbent was ammonia and water system, for 1 TR system, this was minimum collector area 19.85 meters square. COP was this. Okay, comparatively not very high. But in case of parabolic trough collectors, see the difference. For 5 times cooling load, minimum collector area is what? Around say 3 times. But see the efficiency, COP improvement, that is huge. That is huge. That's great. So that is the difference we may achieve with the help of parabolic trough collectors. So by managing the systems, converging the systems in a different way, we may get a better efficiency, or the efficiency measure COP. So the solar absorption system required a large area of stationary collectors such as a plate collector, evacuated tube collector to cool residential places with low cooling loads. The parabolic trough collector is a more efficient for solar heat energy gain in the areas with suitable direct radiations in compared to the evacuated tube collectors.